Hello friends, welcome back to the lectures of thermodynamics. In the last lecture we have seen application of first law of thermodynamics, that is delta Q. You know the first law of thermodynamics, that is delta Q is equals to delta U plus delta W. We have applied this first law of thermodynamics to various types of closed systems. In earlier lecture we have seen application of this law to the constant pressure process, constant volume process, then isothermal process, and in the last lecture we have seen how this law is applicable and what are these terms. Different terms are related to each other in reversible adiabatic process. We say it as the asentropic process as well as the polytropic process. Now in this lecture we are going to see the application of this law, the first law of thermodynamics, to open system, or we say it as flow system. Since in closed system the system is entirely closed, no matter can cross the boundary, so whatever the energy possessed by the system, there were only only one interaction was there between the system and the surrounding, that is the energy interaction. For a closed system, either the heat transfer will be there or work transfer will be there, whereas the matter was remaining same. Matter was not flowing out of the system or flowing into the system, so we were not considering energy possessed by the matter or say the working substance. But in flow system or say in open system, what happens is the matter, the mass continuously crosses the boundary and goes into the system. At the same time, some other mass continuously keeps flowing out of the system. So while the mass, the matter, while flowing into the system or out of the system, it possesses some of the energy and takes it into the system or take it out of the system. For example, if I take down one steam engine or say steam turbine, what happens is while steam turbine is an open system. So while steam turbine is running, what happens? The steam, which is having very high pressure and temperature, comes through a pipeline and enters into the system, that is into the turbine. It gives some impulsive or say reactive effect onto the blades of the turbine, and finally some part of the enthalpy of the steam is get converted into the mechanical work of the turbine shaft. And after having all that energy conversion, the steam comes out of the turbine through another pipe, and that will be given to some other system. So if you take down, if I draw the diagram of that, say this is the turbine and this is the steam going in and this is the steam going out. If I consider this control volume this much as the system, or say not this much, if I consider this much as the system, this is the thermodynamic system, then the mass is crossing the thermodynamic boundary at here and the mass is coming into the system. At the same time, some mass is going out of the system from this point. Whereas there will be some work transfer, work will be going out of the system, the heat will be going, whether going or not, it depends, like whether is there any heat transfer taking place over here or not. So that we will consider, we can assume it to be equal to 0, but work transfer will be there, and out of that one main concern is mass is crossing the boundary, it is coming in, and the mass is again crossing the boundary over here and it is going out. So while that mass is flowing into the system or out of the system, that steam or say that mass possesses some energy, and that energy is also flowing in and flowing out of the system along with the working substance. So that energy also we need to consider while we are applying the first law of thermodynamics to such kind of open system. Now let us see how to apply it. And after applying that, whatever the equation we are going to get, we say it as the steady flow energy equation. But again, before we go to the steady flow energy equation, we need to understand one more important concept that we say as the flow work. Flow work or flow energy. Flow energy, right? Now, what is flow work? I think in the previous lecture someone has commented that why flow work is not present in case of closed system. You will get the answer to that question maybe in this lecture, in this topic. Now let me tell you what is this flow work. In a case if we are having a system like this is any thermodynamic system, compressor, an engine, or a steam engine, steam turbine, anything, and somewhat pipe is connected to this one so as to take down the working substance into the system. The mass is coming into the system through this pipe, and from other end the mass is going out of the system, say from here, and the rate of flow of mass somewhere over here is say m dot, I mean whatever the rate of flow of mass at section 1, if I take down this as the section 1 and this as section 2, so same will be the mass flow rate of the fluid or say that working substance out of the system. Now see, this system will have somewhat internal energy, will have somewhat work transfer, will have somewhat heat transfer some other end, will be having somewhat mass flow rate coming in, mass flow rate going out, but along all these things, mass flow rate which is coming in and mass flow rate going out, both will be having somewhat energies nearby them, but the energy related to the flow of this fluid. For example, if there is somewhat fluid, say the steam over here, and that steam is flowing through this pipe and going towards the system through this pipe. Now if I consider any of the section over here, any of the section of the fluid and some region of the fluid, say like this much region of the fluid, if I take down this much region of the fluid, this much fluid element, rectangular fluid element, will be having somewhat pressure, will be having somewhat volume, mass and all thermodynamic properties. Now while the fluid is flowing, it's not like it's something going on automatically or something flowing by its own without consuming any energy. It doesn't happen. So what has to be done? The fluid over here has to exert somewhat force over here onto this layer. Imagine that this is a small fluid element, rectangular fluid element, and there is a fluid is flowing, and in the flow itself we have considered this fluid element. One of the section of this fluid element, consider a piston over there, consider a piston over here, and that piston is applying a force onto that fluid element so as to push it into the system. So it is not easy for this piston to push it ahead, since this fluid element also has somewhat pressure, right? So this piston has to overcome the pressure force exerted by this fluid element over this side, and in order to push it ahead and push it into this control volume or say into this system, this piston has to exert a force over here, and that force over here, let us say it is the force F. Now obviously we know the term pressure P is equals to the force per unit area. So from this I can take down the term, from this I can take down the force F as equals to the pressure P into the area of cross section. So whatever the force exerted by this imaginary piston onto this small fluid element to push it ahead into the system is F, and that is equals to P into A. So that is what the force exerted by the imaginary piston, or say it actually in a physical sense there is no piston as such over here, there will be other fluid that will be pushing that fluid element ahead. So the force exerted by the fluid behind is equals to F, and that is equal to P into A. Next, now consider that for a small period of time this fluid is get displaced by somewhat amount. Let us say for to push this fluid entirely into the system, this section has to get displaced by somewhat distance, say somewhat distance x. So how much is the work done by this force? Work done by the force will be equals to, this work done by the force will be equals to, we know that is, it is always equals to force into the displacement. I am not going to consider the cos factor over here, since theta in this case will be 0, since both the force and the displacement are in the same direction, so theta will be 0, so cos 0 is 1. So that part is neglected. So the work done by the imaginary piston or say the fluid behind that fluid element is equals to the force into the displacement. Force is F, displacement is x. So this is equals to, I can write down force F is nothing but what are the pressure at here multiplied by the area. So it will be the pressure P into the area A into the term x. Now in this term, P is the absolute pressure and A is the cross sectional area and x is the displacement of the fluid. If you check out this is the cross sectional area and this is the displacement of the fluid, which is nothing but totally the volume of the fluid element which is displaced. So I can write down, instead of this A into X, I can write down this W is equals to, it is P into the volume of the fluid element V. Remember, that is capital V, which is the total volume of the fluid element. So I can write down the flow work, the total flow work is equals to, it's P into the term V. We say it as the flow work. This is the flow work, right? If I divide the entire equation by the letter small m, which is nothing but the mass of the fluid, what I will get is, this will be capital W is equals to P into capital V divided by, divided by small m divided by small m. So out of this capital W by small m, this capital W is the total flow work, W by small m will be the total flow work per unit mass of the fluid, and I can write down this as equals to small w, the specific work done, specific flow work is equals to the pressure P as it is, the absolute pressure, into, what is this term? Capital V is the total volume divided by small m is the mass of the fluid. So volume per unit mass is nothing but the specific volume that is represented by small v, and this is known to be what? The flow work. This is flow work per unit mass of the fluid. This is the flow work per unit mass of the fluid. We also say it as the flow energy, we also say it as the transport energy, since this is the energy related to the transportation of the fluid from one place to another place. By the way, this flow work is present into the fluid which is flowing into the system. At the same time, the flow work is present over here also, since this fluid element is also flowing ahead and going out of the system, and it is not by its own, it's not happening anything automatically. There has to be somewhat force acting onto this fluid element, and that force will push it ahead and kick it out of the system. And for to do that, the fluid left to this fluid element has to do somewhat work, and that work leads to displacement of this fluid element ahead and ahead into the pipeline. And that work done, we say it as the flow work, or say the flow energy, or say the transport energy. And the equation for that flow work is P into V, or P into small v will be the flow work per unit mass of the fluid element. Now just I said, someone commented into the chat box that why the flow work is not present in case of closed system. In case of closed system, remember that this flow work is totally based upon, or say it is totally related to the energy possessed by the flowing fluid. The fluid must be in flow. For example, there is somewhat pipeline and some water, or say the steam, or say any gas is flowing through that pipeline, will be having somewhat pressure and having some certain velocity, certain volume. So if the fluid is flowing through the pipe, then only that fluid will have somewhat flow energy, or say flow work. But in case of closed system, say if I take down a closed system like, say this is a turbine, or say any device like compressor or engine, anything, and it is running, and if I cut down the supply over here, now before I cut down the supply, there was somewhat fluid flowing into the system, fluid going out of the system. So there will exist flow work over here, and obviously this system will be open system, since the mass is crossing the boundary here as well as over here. But the moment when I cut down this supply and cut down this supply also, so as to restrict the flow of working substance into the system or out of the system, in that case this system will become closed system. And the moment when this system will become closed system, there will not be any flow work over here. The system, or say any of the fluid, need not to perform flow work onto the other fluid so as to keep it flowing. And that is the reason, in case of closed system, we do not consider the flow work. Right? So remember this equation, the flow work, small w, specific flow work, small w, we represent it by P into small v, that is the specific volume. Now Let us go ahead for the next topic, that is steady flow energy equation. Steady flow energy equation, abbreviated as the steady flow energy equation, is one of the form of first law of thermodynamics when it is applied to the flow system or say open system. I already told you that whenever there is an open system, then we need to obviously, while applying the first law of thermodynamics, we need to consider delta Q, the first law of thermodynamics, you know, delta Q is equal to delta U plus delta W. We need to consider delta Q, that is the heat transfer taking place from the system, delta U, change of the internal energy of the system, and delta W, that is the work transfer across the system boundary. So all these three parameters we need to consider, but along with that we need to also consider the energy possessed by the fluid that is coming in and going out. At the same time we need to also consider the flow work possessed by the fluid which is coming into the system and going out of the system. And if we combine all these parameters together, we will get one more form of the first law of thermodynamics, and we say it as the steady flow energy equation, right? Remember that this is only applicable for steady flow of the fluid. I mean, in case of unsteady flow, that equation will not get balanced. So let us see what is that steady flow energy equation. For example, there is one thermodynamic system over here which has somewhat inlet pipe at here, and the fluid is coming into the system through any one of the section. So section 1 over here, and the outlet of the system is somewhere over here, from where there is some fluid going out of the system, and I am going to take down the section over here as section 2. Now the fluid properties across section 1, I am going to take down it as U1 as the internal energy across section 1, then Z1 as the potential head or say the total head above the datum level, then C1 as the velocity or say the speed of the fluid element over there, and small v1 as the specific volume of the fluid at this section 1. P1, small p1 will be the absolute pressure of the fluid at the section 1. So these are the fluid properties at section 1, and in the similar manner at section 2 the properties will be U2, Z2, C2, V2, P2. So these will be the properties of the fluid which is going out of the system through this pipe at section 2. So at section 1 we are having one set of thermodynamics properties, we labeled it as by the suffix 1, and at section 2 we are having another set of thermodynamic properties which are labeled with the suffix 2 over there. At the same time there is somewhat heat transfer taking place into the system, let us say it is Q, and there is somewhat work transfer that is taking place across the system boundary, let us say it is W, right? Now let us apply the first law of thermodynamics to this open system. Obviously you can understand this is the open system. Since there is somewhat mass flow rate which is coming in, I am going to take down it as m dot. M dot, that is the rate of flow of mass which is going into the system, is m dot. And what do you think? What will be the mass flow rate which is going out of the system? How much it should be? It has to be m dot only. Since we are considering the steady state condition. Steady means what? It is stable, no property changes with respect to time, right? In a case if this m dot over here is not equal to m dot, means what? The mass flow rate of the fluid which is going in is not equal to mass flow rate of the fluid which is going out. इसका मतलब ये है कि like for example if I take down the mass flow rate over here is say about say 10 kg per second. I mean at every 1 second 10 kg of fluid is coming in, and mass flow rate over here is say it is 8 kg per second. So incoming is 10 kg per second, at every second 10 kg is coming in, and at every second 8 kg is going out. It means that there will be accumulation of 2 kg per second into the system, and the mass of the system will keep on increasing. So if it is a cyclic process, it can't happen, it shouldn't happen actually. right? So for to balance up all the things, we must have the mass flow rate coming in and mass flow rate going out has to be the same, and we have taken it to be equal to m dot, right? Now let us apply the energy balance equation to this system. Now one thing is clear, if we need to balance up our entire system, then the energy flowing in, whatever the energy that is coming into the system has to be equals to energy going out of the system, and obviously then only we can say it has the steady state condition, otherwise it will not be steady state. If the energy coming in and energy going out are not equal, in that case what will happen, either energy will be get accumulated inside the system per unit time, or the energy level will goes down. It depends upon whether the energy coming in is more or going out is more. So it depends on that. So again, coming back to the same point, considering the steady state condition of the system, we can say that energy flowing in, the energy flowing in it has to be equals to the energy which is flowing out. Energy which is coming in has to be equals to energy which is flowing out. So what is the energy coming in? Energy coming in is nothing but the energy possessed by the fluid which is coming in plus the flow energy, or so the flow work that we have just seen, plus the heat which is get added into the system. That will be the energy coming into the control volume. If I consider this as the control volume, then what are the energies which are coming in? So I will say the energy is possessed by the working fluid which is coming in, plus the flow work possessed by the working fluid which is coming in, plus the heat which is going into the system. What are the energies flowing out of the system? That I will say it as, first the energy possessed by the fluid which is going out, then the flow work possessed by the fluid which is going out, and then plus work which is get transferred by the system to the surrounding. So that will be the energy which is going out. Now let us add up all these together. Say first of all, on the left hand side, let us have the energies which are going in. Now energies which are going in, by the way, all this small u is what all these will be the specific properties, that is per unit mass properties, right? Now let us take down the energy of the fluid which is possessed by the energy of the fluid which is going in, and that is, I will say first of all, let us take down the internal energy. Internal energy is U1 plus the specific potential energy per unit mass of the fluid will be equals to GZ1 plus the kinetic energy per unit mass will be C1 square by 2. So this is what, all these are the energies, which type of energies? Internal energy per unit mass, potential energy per unit mass, kinetic energy per unit mass. All of you know this for kinetic energy is half mv square. So if you divide that by m, so it will be half mv square. This will be mgh. This will be, energy per unit mass. So this is energy per unit mass. So we need to multiply it by the term m dot into all these terms, plus again this m dot into the flow work. What is the flow work? Flow work is obviously, this is P1 into V1 plus, see, we have taken the energies of the fluid which is coming in. This is the first term. The second term is what? The flow work possessed by the flowing fluid plus the heat energy which is coming in, that I can say it as dq by dt. It has to be equals to, now this is the left hand side. What will be the right hand side? Right hand side will have the similar terminologies over there, and that will be equals to, it will be m dot into the internal energy across section 2 will be U2 plus GZ2 plus C2 square by 2 plus this is mass flow rate going out into the flow work across the section 2 will be P2 V2 plus work transfer dW by dt, right? Now if I take down this in simplified form, what I will get is, see, into the first term and into the second term I can take down m dot as common. So what I will get is m dot, that is mass flow rate which is going in, into this U1 plus this term, U1 plus P1 V1 plus GZ1 plus C1 square by 2 plus this is dq by dt, that is the rate of flow of heat into the system with respect to time. Now the terminology is on the right hand side. Again over here onto the right hand side also I am going to take down m dot as common, that is mass flow rate of the fluid which is going out. This will be U1 plus P1 V1 plus GZ, sorry, it's not 1, it is 2, since we are taking down these properties across the section 2. So GZ2 plus C2 square by 2 plus dW by dt, that is the rate of transfer of work out of the system. So out of that we know this U1 is the internal energy per unit mass of the fluid at section 1, P1 is the absolute pressure and V1 is the specific volume, and we know that U plus PV, P into V, this is internal energy plus flow work, we say it as the enthalpy H of the system, enthalpy H of the fluid. So I can also write down, if this is the equation, if enthalpy is nothing but the sum of internal energy and flow work, I can apply it to across this point. So I can write down this as U1 plus P1 V1 as equals to H1, that is the enthalpy across section 1, and also U2 plus P2 V2 will be equals to H2. So if I put on these values into this equation, what I will get is, this is m dot into H1. Now instead of U1 plus P1 V1 I can write down H1, which is nothing but enthalpy of the fluid across section 1 plus GZ1 plus C1 square by 2 plus this is heat transfer, that is dq by dt, is equals to m dot into, now again U2 plus P2 V2 I can replace this term by the term H2, where H2 is nothing but enthalpy of the fluid across the section 2, that is again the specific enthalpy, that is enthalpy per unit mass of the fluid across the section 2, that is H2 plus GZ2 plus C2 square by 2 plus again this is dW by dt. So this is one important equation. Now let us divide the entire equation by the mass m. So what I will get, this is basically one of the important equation of one of the important form of the steady flow energy equation. Now apart from that, if I divide the entire equation by the letter m, small m, which is nothing but what, the mass flow rate of the fluid, then what equation I can get is, that will be, this will be H1 plus GZ1 plus C1 square by 2 plus, now let us take down this as equals to q dot, is equals to q dot is, dq by dt can be taken it as q dot, is equals to, this is H2 plus GZ2 plus C2 square by 2 plus W dot. Actually this has to be small q, since if we divide, this can be taken it as directly q dot, capital Q dot, but capital Q dot divided by small m will be small q dot. That's what the heat transfer rate taking place per unit mass, work transfer rate taking place per unit mass. So this is one more equation for the steady flow energy, steady flow energy equation, one more form of steady flow energy equation. Remember that while you are applying the first law of thermodynamics to any kind of flow system or say open system, for example compressor for internal energy, steam turbine, gas turbine, steam engine, then centrifugal pump, hydraulic turbine, anything which is open system. So while you are applying the first law of thermodynamics to the open system, then you need to follow this equation. either this equation or this equation. Since in open system the mass is continuously crossing the boundary, and as the mass is crossing the boundary, there will be somewhat energy crossing the boundary along with the mass of the fluid. I mean, apart from this energy Q and W, there will be other energies also which are coming in and going out of the system, and that also we need to consider, right? And if we consider the energies possessed by the fluid which is coming in and the energies possessed by the fluid which is going out, and if we count up these energies also, if we consider these energies and if we balance up the equation for the steady state condition, what are the expression we have derived, finally you will come to this equation, and we say it as the steady flow energy equation. This is again one more form of the first law of thermodynamics. Now in the next lecture we will see how to apply the steady flow energy equation to different kind of open systems that we encountered in that we come across in mechanical engineering. Not simply mechanical engineering, but in day-to-day life, whatever the open system we come across, we will apply this equation, steady flow energy equation, to these systems. And finally, after applying this equation, we will get very simple and short equation to that particular system. Like for example, for turbine, only W will be equal to H1 minus H2 will be the equation. So whatever the enthalpy change of the working fluid across section 1 and 2, that is equals to the work transfer. If we assume rest of the parameter like work transfer is 0, if we assume the potential head potential difference is 0, or say it's negligibly small, then we can assume so, and we can get finally simple equations with the aid of which we can analyze that thermodynamic system, right? So for today we will stop over here. Thank you.